Patty Simpson with Simpson Math. In this video, we will learn about the hypergeometric distribution. And the hypergeometric distribution is just a discrete probability distribution. In other words, our random variable will be countable. It's a discrete probability distribution where we have a population of items and we're going to select from that population a sample, and we're going to do that without replacement. So that's the first thing that we're looking for, is that it's done without replacement. In the past, we've looked at the binomial distribution. In that case, it was always with replacement, or our probability stayed the same in binomial. But in hypergeometric, it will be without replacement, or our probabilities will be dependent upon one another. Here we also have the number of trials in our experiment is fixed. It's a set number of trials. There will still be two possible outcomes from each of our trials. We'll call one a success and the other a failure. Sometimes we just are able to split it into two groups. We call one success and one failure. In this video, I'm just going to give you three examples of a hypergeometric distribution, and we'll look at how each one of those is met. Here's the first example. Given an urn with 8 balls, 5 green and 3 white, 4 prisoners must draw from the urn without replacement. The guards execute the prisoners who draw a green ball. What's the probability one prisoner is selected? In this case, we do have a population of balls that we're going to choose a sample from, and we're going to do that without replacement. The number of trials in this experiment is fixed. There are 4 prisoners, so those 4 prisoners are the number of trials. They're each going to draw out a ball. It is a discrete distribution. Our random variable is the number of green balls that we choose, and we can count the number of green balls that we choose, 0, 1, 2, 3, or 4. Then there are 2 possible outcomes for each trial. We either are going to draw a green ball or a white ball for each one of those trials, a success or a failure. Here's another example. 5 police officers and 20 firefighters attend a conference. All 25 names are put in a hat, and 5 names are randomly picked without replacement. What's the probability that 3 police officers and 2 firefighters are chosen? Again, we have a population of 25, and we're going to select a few out of there without replacement. This is a discrete variable because we're going to be counting the number of police officers that we choose out of the hat. We could choose 0, 1, 2, 3, 4, or 5. The police officers are countable. Those names are countable. So then the number of trials is fixed. We're going to pull out 5 names. So the number of trials is 5. And we have 2 possible outcomes. We're either going to pull out a police officer or a firefighter. Assign one of those success and the other failure as your 2 variables, or your 2 outcomes from each trial. So that is hypergeometric. Our last example, Miss Stash is very organized. She keeps 4 knives with Tiny Tim's 16 toys in the playroom bin. Tiny Tim blindly selects 3 items from the playroom bin without replacement. What's the probability Tiny Tim selects at least 1 knife? So here again, we have a population of items in the playroom bin, and we're going to select a sample from there. We have a fixed number of trials. We're going to select 3 items out, and it is without replacement. And then we have 2 groups, success and failure. We have our toys and our knives that we are going to pull out of the bin. So all 3 of these are examples of hypergeometric distributions. In the next video, we're going to look at the variables of the hypergeometric distribution. In this video, we're going to look at the variables of a hypergeometric distribution. In the previous video, we looked to see what makes a hypergeometric distribution a hypergeometric distribution. And we saw that for a hypergeometric, what we are doing is taking a population and collecting from that a sample without replacement. So here, our population size is a capital N. We're going to denote it with a capital N. And then that sample size that we are choosing we're going to denote with a lowercase n. We've seen that in the past in statistics, that when we refer to our population, we use a capital N, and when we refer to our sample, we use a lowercase n. Then, we also discussed in the previous video how we were going to have two choices, or two options for each outcomes for each trial, a success and a failure. Here, our K, we're going to denote with a K the total number of those successes that we have within our population. And then our X, our random variable, is going to be the number of those successes that we are going to choose. So these are the four variables that we're going to look at. And in the next video, then we'll use these variables in the hypergeometric distribution formula that helps us to determine the probability. But here, let's just start by finding what is our population. So the total number of balls that are in the urn. And that total number of balls, or our population, is 8. The sample size is the number that I'm going to pull out. How many am I going to remove without replacement from the urn? And we are going to remove 4, because our 4 prisoners are all going to draw out a ball. So our sample size here is 4. Then K is the total number of successes. Well, our successes are the prisoners that are executed. We're looking for those ones that are executed. And in order to be executed, you draw a green ball. So here our greens are our successes. And we have a total of 5 greens within this population. And that's what our K represents, is the total number of those successes. Then the X is how many of those successes am I looking for? How many of those successes do I want to choose? And I want only one of my prisoners to choose a green ball. I want only one to be successfully executed. So my X, my random variable there that I'm looking for, is 1. Let's do the same thing with our 5 police officers and 20 firefighters that went to the conference. So we had our population here of 25 different officers. And of those 25, the sample that we're looking at, or the number of names that we're pulling from the hat, our sample are the 5 names that we're pulling from the hat. So we have 25, but we're just sampling 5 of them. And again, we're doing it without that replacement. Our K, or the total number of successes we have, well, here we have 3 police officers and 2 firefighters. You can really pick which one you want to be the success or not. In this case, maybe since police officers are first, we'll go with the police officers as our successes. But we could do this just as well with firefighters, and it would work just as well. So here, we'll call the police officers my successes, in which case I have a total number of 5 police officers. That's our total number. But of those, I am only choosing 3 of our police officers out. We only want to choose 3. So here my random variable then is 3. On our last one, Miss Stash and Tiny Tim is pulling out of a whole collection of objects in his playroom bin. The entire collection of objects in his playroom bin make up the population. And he has a total of 4 knives plus 16 toys, gives me 20 total objects in that playroom bin. So his population size is 20. The sample is the number that he is pulling out from that population. And here he is pulling out 3 items from the playroom bin. He's going to remove 3. So 3 is the number in our sample. That's how many he's removing from that entire population. Then we have to decide on our success and our failure. And since we are choosing a knife, we're looking for the probability of the knife. Let's make the knife our success there. Again, I could use the toys as my success and it would work just as well. But since I am looking for my knife, I'm going to go ahead and stick with my knife. The total number of knives in the population there is 4. And of those, I want at least 1 knife. Now let's look at these words, at least 1. So remember that if my doctor tells me that I have to have at least 1 pill a day, that means I could take 1 or 2 or 3 or more. At least 1 means 1 or more. If you should put on at least 1 bandage a day, it means 1 or more. So in this case, if I'm going to get at least 1 knife, then Tiny Tim could get 1 knife, or he could get 2 knives, or he could get 3 knives. Now, the most he can get is 3 because he's going to pull out 3 from that playroom bin. So even though there are 4 knives in there, the most he can get is 3. And to find this one, we're looking at not just 1, but because it's at least 1, our random variable is 1 or 2 or 3. Notice that the only thing missing from this is 0. We may use the 0 as the complement of at least 1. So we may use the complement when we're actually using the formula to help us out. So that's how we find the random variables within our hypergeometric distribution. In the next video, we're going to use the formula to actually solve for the probabilities. In this video, we're going to use the formula for the hypergeometric distribution to solve probabilities. In a previous video, we looked at what made a hypergeometric distribution hypergeometric. And we saw that we needed a population of items that we were choosing a sample from, choosing a few from, without replacement. We're going to use a capital N to denote our population size and a lowercase n to denote our sample size. We've done that in the past in statistics. We use a capital N to represent how many are in our entire population, in our entire group. And the lowercase n we use to denote how many we're choosing from that, how many of those we're choosing out. We're going to do the same here. Here, our K is the total number of successes. So in that previous video, we saw that we could divide our objects into 2 groups, successes and failures. And the total number of successes, we're going to denote with a lowercase k. And then from those total number of successes, we're going to be looking for some of those to be chosen, which will be our random variable of x. And then the formula, well, with probability, our total number is always on the bottom or in the denominator. And here we have the total number of ways that our sample can be chosen from our population. And this is the combinatorics formula, or the combination formula, and we'll look at that here in a second. And then on top, this is the number of ways that we can choose our successes, the number of successes we're going to choose from our total number of successes. And we're multiplying that times, well, when we do the population minus our total number of successes, that's going to give us our total number of failures. And from that, we're going to choose a certain number of those failures. So that'll be on bottom. These guys, this bottom and this bottom, should always add up to be our sample size. And this number plus that number should always add up to be our population size. So let's take a look at how this formula will work. First thing we need to do is recognize what are those numbers. So let's look first to find our population size, our sample size, our total number of successes, and the number of successes we're going to choose. So the total population here, We have a whole group of balls. So it says, given an urn with 8 balls, 5 green and 3 white, 4 prisoners must draw from the urn without replacement. The guards execute the prisoners who draw a green ball. What's the probability? Only 1 prisoner is executed. So we have a whole population of balls, and there are a total of 8 of them. That is our population size. From those, we are only going to choose, well, it tells me that I'm going to have to draw from the urn 4 of those balls. Each prisoner is going to draw a ball. So 4 are going to be chosen from the urn. Then my K is the total number of successes. So here I have to decide what is my success and what is my failure. I'm looking for 1 prisoner to be executed. So my execution there is going to be my success. That's what I'm looking for. I know it seems a little morbid, but that's how sometimes it works. Our successes sometimes are kind of morbid there. So that's just what we're looking for. And in order to be executed, they have to draw a green ball. So I'm looking to see how many total green balls there are in my population. And there are a total of 5 green balls. So my K in this one is 5. Then how many of those green balls do I want? Well, I want only 1 prisoner to be executed. So I'm only looking for 1 of those green balls. Now I'm just going to fill into my formula so that I'm looking for the probability that 1 prisoner is executed. Maybe you've seen it like this before, where your X equals 1. Then on the bottom of my probability is always the total number of ways. So we're going to look for how many ways can I pull 4 balls from the 8. Then in my numerator, I'm looking for the number of ways that I can get 1 green ball from my 5 balls. So here I have 5 balls and I'm choosing 1 of them. But I was choosing 4 balls. So that means that also on top, I'm going to have some failures that I'm choosing. Well, how many total failures are there? Well, there are 3 of my failures, 3 of those white balls. And then in order for me to get only 1 green ball, that means the rest of mine have to be white, or I can subtract 4 minus the 1 to get 3 of them to be white. So if one prisoner draws a green, that means the other 4 have to draw the white. So now I'm just going to do my combinatorics, or my combination there. I'm going to plug that in. Remember, that's 5 factorial over 1 factorial times 5 minus 1 factorial. Here, this is 3 factorial over 3 minus 3 factorial over 3 factorial. On bottom, I'm going to have 8 factorial over 4 factorial over 8 minus 4 factorial. Now, when we do this work, we're going to end up with just 5 on top. Anytime we're choosing 1, we just end up with that top number. When the 2 numbers are the same, we always just end up with 1. Or you can do the work out here to find out that that's just going to be a 1. On bottom, though, it's a little more complicated, so that I have, I'm going to do this subtraction to get 4 factorial. And then this 4 factorial, I'm going to write out as 4 times 3 times 2 times 1. Then my 8 factorial, I'm going to count down until I get to that 4 factorial. So I've got 8 times 7 times 6 times 5 times 4 factorial. My 4 factorials cancel. I'm going to do a little bit more simplification down here on bottom. Notice that 3 times 2 gives me 6. So I'm going to notice that this 6 divided by that 6 equals 1. Then this 8 divided by that 4 gives me a 2. This 8 divided by that 4 gives me a 2. Every time it should work out this way so that I don't have anything in this bottom denominator. I should be able to simplify until there's nothing left down there. So on top I have 5, and in the denominator right now I have 2 times 7 times 5. 2 times 7 times 5. I'm going to continue to simplify before I multiply, so that, notice this 5 divided by that 5 becomes 1. And then I'm just left with 1 on top and 14 on bottom. So the probability that only one prisoner is executed is 1 out of every 14 times that 4 prisoners draw the balls from the urn. So that's how we use the hypergeometric distribution form. In this video, we're going to do an example of the hypergeometric distribution. So in previous videos, we looked at what made a hypergeometric distribution hypergeometric, and we looked at the variables and formula of that hypergeometric distribution. In this one, we're just going to do this example. 5 police officers and 20 firefighters attend a small conference. All 25 names are placed in a hat, and 5 names are drawn without replacement. What is the probability 3 police officers and 2 firefighters are chosen? So we saw with hypergeometric distributions that we have a population and we're choosing a sample from it. In this case, our population size, or the whole total group, is 25. So our N will be 25. And from that, we will be choosing a sample. Well, all 25 go in the hat, but only 5 are chosen. So 5 here is our sample. Then, our total number of successes, well, this one's a little bit weird because we have 2 different ones that we could make. Actually, all of our hypergeometrics could work this way, where we could choose one or the other to be our successes. Here, we could either choose our police officers to be our successes, or we could choose our firefighters to be our successes. In the end, it doesn't actually matter. We'll go ahead and, since our police officers are first, we'll use those as our successes, but you firefighters out there, just know you're just as much of a success. All right, so our total number of successes then are the 5 police officers, and from those we are choosing 3 from those 5. Now we're going to fill in our into our formula now. On the bottom, on the top of our formula, first we just put in our probability. Our X value goes in here, so in this case we're looking for 3 police officers to be chosen. On the denominator of all our probabilities, we put the total number of ways. Here we're going to put the total number of ways that 5 names could be chosen from the total of 25. So that's what goes on bottom, is the total number of ways we can choose those 5 names from our population. On top, we want to draw 3 police officers out of the 5 police officers that we have. So we have 5 and we want to choose 3. So we're using that combination to help us do 5, choose 3. Then we're choosing 5 names and we've only looked at 3 of them. So the other 2 are firefighters. So 5 minus 3 gives me 2. I want to choose 2 firefighters. And then how many total firefighters did I have? Well, 25 minus 5 gives me the 20 firefighters that I have. So here's the total number of police officers and the police officers I'm choosing from those, the total number of firefighters and the number of firefighters we're choosing. And then this is the population and our sample that we're choosing out of there. Notice that we could have swapped these 2. We could have put the 20 choose 2 times the 5 choose 3 because multiplication is commutative. So that's what I mean by you could make your success either one. Now we're going to work these out. Hopefully you know that combination formula. You're going to need it. The 5 factorial over 5 minus 3 factorial times 3 factorial. I'm multiplying that times 20 factorial over 20 minus 2 factorial. And then don't forget the 2 factorial out front. Then in the denominator, I have 25 factorial on top, and 25 minus 5 factorial. If I left it like that, that would be the permutation, remember. I've got to stick this 5 factorial out front so that I have a combination. Now, I'm just going to work through this and simplify as I go. So here in the denominator, I'll move over here to the left, see if you can follow from there to here. I'm going to do 5 minus 3 gives me 2 factorial, and then this is 3 factorial. On top I have 5 factorial, and remember that means 5 times 4 times 3 times 2 times 1, or I can do 5 times 4 times 3 factorial, because that 3 factorial means 3 times 2 times 1. This 3 factorial on top and that 3 factorial on bottom are going to become 1. This 2 factorial on bottom really means 2 times 1, just 2. 2 does divide into that 4, so I can simplify that to say this 2 divides into that 4, and it leaves me with a 2. So here on top, I'm just left with 5 times 2. Now that was this first part. Now I'm going to do the next part. I'm going to do 20 factorial. Well, let's start on the bottom. 20 minus 2 gives me 18 factorial. And then here I have 2 factorial. Again, with that 20 factorial, it's 20 times 19 times 18 times 17 times 16, etc., etc. Or I can just stop at this 18 factorial, and this 18 factorial on top and that 18 factorial on bottom become 1. This 2 factorial is really 2 times 1, and 2 times 1 is just 2. 2 goes into 20 10 times, so that I have a 10 there up on top. So I'm left here with, on top, I'm going to have 5 times 2 times 10 times 19 in my numerator. 5 times 2 times 10 times 19 in my numerator. Then in my denominator, I have that 25 factorial. Well, let's start in the denominator again. 25 minus 5 gives me 20 factorial. I'm multiplying that times 5 factorial. I'm going to go ahead and write that out. 5 times 4 times 3 times 2 times 1. On top, I'm going to count down from 25 until I get to this 20, so that I have 25 times 24 times 23 times 22 times 21 times 20 factorial. The two 20 factorials become 1. And now I'm looking for ways to reduce. I know from doing combination that these should all be able to divide into those top numbers. So 5 goes into 25 5 times. And then notice that 4 times 3 is 12, times 2 is 24. So what I have left on the bottom here is 24. I can just take that 24, 4 times 3 times 2, that 24, and divide it with the 24 there. So then, notice I have nothing left in the denominator here, but in this denominator, I'm left with 5 times 23 times 22 times 21. In that same spirit of simplifying before we multiply, I'm going to look for further things that I can simplify. Notice that there's a 5 on top and a 5 on bottom, so that becomes 1. Also, that 2 divides into that 22 11 times. Now that's prime. 7 times 3, neither one of those has a factor of 7 or 3. So I've done simplifying. Now I can just multiply. And I'm left with 10 times 19 is 190. And 23 times 11 times 21 is equal to 5,313. So the probability that exactly 3 police officers and 2 firefighters are chosen is 190 over 5,313. So there's an example of our hypergeometric distribution. And in this video, we're going to do an example of the hypergeometric distribution. We've seen in previous distributions what makes a hypergeometric distribution, and we've talked about the formula and the variables for that hypergeometric distribution. Here we have an example. Mrs. Stash is very organized. She keeps her 4 knives with Tiny Tim's 16 toys in the playroom bin. So we have a population of items in the playroom bin. In fact, we have a total of 20 items in that population. So our n in this example will be 20. Our population size will be 20. Tiny Tim blindly selects 3 items from the playroom bin without replacement. That without replacement is what makes that hypergeometric rather than binomial. The fact that we are not replacing. And here he is selecting 3 items, so his sample is 3 items. So our sample size is 3. Now, we also need to know what is the probability that Tiny Tim selects at least 1 knife. So our K is the total number of successes that we have. In this case, our success is for him to choose a knife. So we want to know the total number of knives in our population, and that is 4. And Tiny Tim is going to choose at least one of those, at least one. So let's talk about what it means to be at least one. So if the doctor tells me I need to put on at least 1 bandage, that means I need to put on 1 or 2 or 3 or more. I can put on 1 or more bandages. So Tiny Tim, if he's going to select at least 1 knife, that means he's going to select 1 or 2 or 3, but we have to stop here at 3 because the most he's going to select out of there is 3. So here our X is 1 or 2 or 3. So in order for us to use this formula, we need to find the probability where X equals 1 plus the probability that X is 2 plus the probability that X is 3. And add all those together. Remember, those ORs tell me to add that together, and then if there happens to be any overlap, subtract that off. Now that looks like a lot of work, so I always start looking for the complement anytime that there's several little things that are involved. Could I use the complement? Well, here we have 1, 2, or 3. What else is in the set of how many knives he could pull out? Well, he could pull out 0 knives. So 0 is the complement of 1, 2, and 3, that at least 1. So 0 is the complement. So we could just say that the probability of this is equal to 1 minus, so let me write it up here, the probability of 1 plus the probability of 2 plus the probability of 3 is equal to 1 minus the probability of 0, because 0 is the complement of 1, 2, or 3. And so if we just subtract that from 1, we'll get that probability. It's kind of like when the weatherman tells you there's a 60% chance of rain, the complement then is that there's a 40% chance that it won't rain. So we can take and subtract the complement to get the probability that it won't rain or that he gets at least 1. So we're going to only have to find the probability of 0 knives. So now I'm going to use my formula. In the denominator, I'm going to put the total number of ways that he could choose 3 items from his 20. He's got a population of 20 and he's choosing 3. And in the numerator, we're going to put what he's looking for, the total number of successes. So he has a total number of 4 knives, but we're going to find that complement, so we just want 0 there. So now, if there are 4 knives or 4 successes in there to make up the 20, well, how many toys are there or how many failures are there? There are 16. And if he is choosing 0 knives, how many of the toys would he have to choose? He would have to choose 3 toys. So now we've filled in for our formula. Notice that 0 plus 3 does equal 3, and 4 plus 16 does equal 20. Those should always add up like that. Now it's just a matter of doing the combinations. 4 choose 0. Hopefully you've had enough work now with combinations that you know when we're choosing 0 items, we're just going to end up with 1 there. 16 choose 3. I'll put in the formula. So I have on bottom, I'm going to have 3 factorial and 16 minus 3 factorial. And on top, I'm going to have 16 factorial. Then in the denominator, I'm doing 20 choose 3. So 20 factorial over 3 factorial times 20 minus 3 factorial. Now it's just a matter of doing some arithmetic. Let me do that for you. So we have, I'm going to do this subtraction first. So I have that 1 times 16 minus 3 is 13 factorial. And that 3 factorial, we could count down 3 times 2 times 1 times the 13 factorial. On top, I'm going to stop at 13 factorial, 16 times 15 times 14 times 13 factorial. And the reason I stop there is so that this 13 factorial divided by that 13 factorial gives me 1. I could continue to simplify. We know that when we do these combinations that we should end up with 1 on our denominator here. So 3 goes into 15 5 times. And 2 can go into either the 16 or the 14. Take your pick. I'll make it go into the 16 to get 8. It doesn't matter. We'll both get the same answer. So in my numerator, I'm going to be left with 1 times 8 times 5 times 14. Now that 1 is, since 1 times 8 is just 8, I'm going to leave the 1 off. So we got 8 times 5 times 14 in our numerator. Then in my denominator, 20 minus 3 is 17 factorial. So on top there, I'm going to stop at 17 factorial. 18 times 17 factorial. I still have that 3. And remember, it's 3 factorial, so it's 3 times 2 times 1. I stopped at 17 factorial because 17 factorial divided by 17 factorial is just 1. Again, we know that we should be able to simplify until the denominator's gone. So this 3 times 2 is 6. And 6 can go into 18. So let's just take this whole 6 on bottom and divide it into 18 to get 3, because 6 goes into 18 3 times. You could have done it differently. You could have said 3 goes into 18 6 times and 2 goes into 20 10 times. It would still be the same in the end. It's okay. So here in my denominator, I have 20 times 19 times 3. Again, I'd like to simplify before I multiply. So if I can, I'm going to look for anything that divides. So notice this has a factor of 5 and this has a factor of 5. 5 goes into 24 times. And this 4 can go into that 8 on top. So 8 divided by 4 is just 2. Now on bottom I have 19 and 3. They don't have any factors in common with 2 times 14. So now I'm just left with 2 times 14 over 19 times 3, or 28 over 57. Now what I've just found is the probability of 0. But we want to know what's the probability that Tiny Tim gets at least 1. So we need to take that, and in order to find out at least 1, we're going to subtract that from the whole set. So now we're going to find the probability of 1 plus the probability of 2 plus the probability of 3, we're going to take the whole set plus 0, subtract off that 0, the probability of 0, and we end up with 29 over 57 is our probability that he gets at least 1 knife. So there's an example of our hypergeometric distribution. Math made simple, it's Simpson Math. Thanks for watching.